Good morning, everyone. Myself, Dr. Afroz Meher, Professor, Mechanical Engineering Department, Chalan College of Engineering Technology. So today we will be dealing with a problem on finite element analysis with respect to one-dimensional bar element. Okay, right? So the problem which we are dealing is determine the nodal displacements for the given step bar. So this is the step bar where the area for the first step is given as A1 is equal to 1500 mm square and area for the second step A2 is 1000 mm square and the length L1 is equal to 200 mm and the length L2 is equal to again this is also 200 mm and there is a force of at this particular node P is equal to 300 kN. So before we proceed for the problem, so we will be discretizing this step bar into nodes and elements. Okay, right? So with respect to this step bar, we will be having, you can generate three nodes. This is first node at this end, second node at this end, and the third node is at the place where there is a section change. Okay, right? So this is node 1, this is node 2, and this is node 3. Okay, right? Our aim is to find the displacement of this particular step bar. So here the displacement which is taking place, we consider it as U1. Here we take it as U2. And here the node, the displacement which is taking it, third node, we consider it as U3. To find the nodal displacement, we need to consider the formula K Q is equal to F. Okay, where K is the global element stiffness matrix and Q is the global nodal displacement and F is the global force vector. So, and your K matrix depends upon the number of nodes. Suppose here and the K matrix will be the square matrix. Here, how many nodes we are having? We are having 3 nodes, right? How many nodes we are having? 3 nodes, and how many elements? 2 elements. This is element 1 and this is element 2. So the size of the global stiffness matrix will be, it depends upon the number of nodes. So your size of your global stiffness matrix will be 3 by 3 matrix. So before proceeding for the calculation of the nodal displacement, we need to calculate the global element stiffness matrix. For that purpose, we will be calculating element by element, then we go for the globalization of the matrix. Okay. So now first of all, we will consider this element, which is having the shading nodes of 1 and 2. Element 1 and the shading nodes are 1 and 2. So the element stiffness matrix for the bar element is KE is equal to EA by LE. This is with respect to element 1 minus 1 minus 1. So this is the formula for calculation of element stiffness matrix of bar element. That is K is equal to AE by LE 1 minus 1 minus 1 where your E is the X modulus, A is the area and L is the length of the element. And suppose if you are calculating for the first element, then what are the dimensions have been given to the values? So suppose if you substitute here, so if suppose as we are calculating for element 1, so it will be E1 A1 by L1 is for K1 first element. So this is 1 minus 1 minus 1 1 where the shading nodes are 1 2 1. Okay. So after getting this formula, we need to substitute here where K1 is equal to E1. What is the value of E1? Suppose we can take E1 is equal to 2 into 10 to the power 5 newtons. So we can take E 2 into 10 to the power 5 and A is how much? A1 is 1500 mm square first element is 200, and you are having the matrix 1 minus 1 minus 1 1, and with the shading nodes 1 2 1. So why we are writing the shading nodes? Why? Because whenever we are going for the globalization of the matrices, it will be easy for us. Okay. So if you see here, if you just remove this 2 2, so the left of is how much will be? 15 into 10 to the power of 5. 1 minus 1 minus 1 1. With the shading nodes as 1 2 1. Okay. This was the element stiffness matrix for first element. Then we need to calculate the element stiffness matrix of the second element. Then next what we do, we will take the element 2. So our K2 will be, K2 is E2 A2 by L2, 1 minus 1 minus 1 1, where the shading nodes are 2 and 2, 2 3 2 3. So after substituting here, so we need to substitute the data to get the element stiffness matrix. So here E2 is how much? E2 and A1, E1, E2 are the same. That is 2 into 10 to the power of 5. And A2 is how much? 1000 mm square. By L2. L2 is how much? This is 200 mm. And same. 1 minus 1 minus 1 1. And the shading nodes are 2 3 2 3. So after getting the element stiffness matrix of 1 and 2, we need to go for the global element stiffness matrix. Okay. So the global element stiffness matrix will be of size 3 by 3. Okay, right? Where we will be having, we can generate this matrix with respect to 3 nodes, that is 1 2 3 1 2 3. Okay. So what are the matrix we got from element 1 and element 2? We need to put it over here to get the element stiffness matrix. Okay, right? So here this is the element stiffness matrix for first element. Okay, right? So what we do first of all, before that, we see that so we have the common value for this, so that it is easy to calculate over here. So before that, we can just go for this. This is 2 zeros. Here we can cut it off. 2 is 4. Here we get around how much? 10 into 10 to the power of 5. 1 minus 1 minus 1. So what we can do, we can keep 10 to the power of 5 common outside, and the other guys we can take inside. So here what we can do is here. The next is here. 10 to the power of 5 we can take outside, 10 is we can take inside. 10 minus 10 minus 10 10 here. So which is having the shading nodes of 2 3 2 3. And in element 1 here also what we can do for ease of calculation, we can take this 15 inside. K by 10 to the power of 5 outside. Here we can take 15 inside. 15 minus 15 minus 15 15. So the shading nodes are 1 2 1. So we are having the element stiffness matrix of element 1 and element 2. Now we can go for the globalization of the element stiffness matrix. Okay, right? So here, as we know that the global stiffness matrix depends upon the number of nodes. So and the element stiffness matrix is a square matrix. So suppose if you are having 2 nodes, the size of the global stiffness matrix will be 2 by 2. If it is 3, it is 3 by 3. And suppose if you are having 5 nodes, it will be 5 by 5 matrix. As with respect to this problem, as we are having 3 nodes, so our size of the global stiffness matrix will be 3 by 3. So first, what we do first, we will be taking the element 1, then we'll substituting over that, then we'll be taking element 2 and substituting over. So if you see here, this 10 to the power of 5 is common here and here. Okay. So what we can take this 10 to the power of 5 common over the outside 10 to the power of 5. First of all, we'll be can just take like this. So you can just keep it over here, 15 minus 15 minus 15. In the same way, you can assemble the second matrix, K2 matrix in global stiffness matrix, that is which is having shading modes of 3 and 2. Here, this is here it is having the shading mode of 2 and 3. This matrix is here, 2 matrix and 2 matrix. So what are the numbers that are having? 15 minus 15 minus 15 15. So this is K1, this is K2. K2 is having 10 minus 10 minus 10 10. So this is plus 10 minus 10 minus 10 and 10. So the left of cells we need to keep it as 0. Okay? Shall I will erase this? So actually our aim is to find the displacement matrix of a stirred car. Okay, displacement we need to find. So we know that to find the displacement, the formula is Q is equal to F. Okay, so we have calculated this, the global displacement matrix, which is having the size of 3 by 3, and this is the displacement matrix where we need to find it. Okay? And this is the force vector. Okay, so force vectors can be applied directly. So we have already calculated. We will substitute here. We can get this matrix over here. So that is 10 to the power of 5. 10 to the power of 5. What did we get this? 15 minus 15. 0 minus 15. 25. This is minus 10, this is 0, this is minus 10, this is 10. Okay, and the loads which they are having is 1, 2, 3, 1, 2, 3. Okay, and as we have taken the standard, the displacement which is taking place at node 1 is U1, at node 2 is U2, at node 3 is U3. So here the matrix will be getting here U1, U2, and U3. These are the unknowns which we need to find. Okay, is equal to the force matrix. Here you see the type of loading condition is only at point loads. So other loading conditions cannot be. Only they are having point load, and point loads are directly applied. Okay, at which node it is having, it is directly applied. If you see here, at node 1 it is fully constrained, at node 2 also we don't have any force. If you see here, node 3 we are having a force which is acting at the right side, x-axis, which is having P is equal to 300 kN. So if you see here, we don't have any load over here. At node 1, it just take the K nodes 1, 2, 3. So at node 1 we don't have any load. Even at node 2 also we don't have any load. But at node 3 we are having a point load of 300 kilometers, and that is which is also acting on the right side. So by default what we consider, suppose if this is the origin, right side, this is x and this is y, this is positive, we consider this is positive 1. And the opposite to this will be considered as negative. So this is your negative x and this is your negative y. If you see here, according to this, the force is acting to the right side, which is having towards the positive end. So here the number which we need to take is the positive one. And if you see here, this is 300 kilonewtons. So that is, we can take it as 300 into 10 cube. Or we can suppose if I want to make it as a similar number, I can take it as 3 into 10 to the power of 5 newtons. Okay. So here I can take 10 to the power of 5 outside. And 3 inside. Okay. The next step is that cutting the single number. So 10 to the 5 and this 10 to the power will go. To find the total displacement, now the next step is we'll be applying the elimination approach method. Okay, right? So let's stop.